measurement theory, this is called a generalized measurement. The requirement is that you need to have this expression. You need to sum to identity, meaning that the probability is conserved. There's no leakage of your measurement. And this POVM, physically, it means that suppose you can design a measurement and you send a spin 3-half particle into your measurement device, and your device tell you that, okay, I get a reading X, Y, or Z. This means that the state after the measurement is projected by the corresponding operator. So sometimes I project into X, sometimes I project into Y, sometimes Z. And the randomness, we have no control. So we have to live with the randomness. And because the measurement gives random outcome, so most of the time, we would like to simulate this distribution. But how do we know the probability of, let's say, a given set of outcome? What is the probability that it can occur? This is actually related to this huge correlation functions. So you have to compute this S square alpha. So alpha depending on what measurement outcome. So for each side it could be X, the other side could be Y and Z, etc. So you need to compute this. Luckily, this can be done by use coherent state method, or you could use tensor product. Actually, you can evaluate this. It turns out this is a geometric object. So the probability of given measurement configuration scale with the 2 to the number of vertices. I'm going to define that later, minus the edges. So this becomes a geometric object. This is going to be useful later when we do numerical simulation. And we prove rigorously that after the POVM on all sides, or the generalized measurement on all sides, the AKLT state is converted to a graph state. And the graph state is determined by its graph. So we need to know how we identify the graph. And once we identify that, we would like to know whether we can construct many paths and also bridges connecting them. If so, then we can use for quantum computation. And notice that this is related to percolation. So we ask whether the graph is percolated. So let me just show you an example. So I show on 2 different lattices. This is on honeycomb, this is on the square octagon. So these X, Y, Z indicate that my POVM outcome, measurement outcome, the device will tell me this is X, this is Y or Z, etc. And it's random, but I know the probability is this. So let me explain. So B here denote the number of region, or we call domain, that has the same outcome. For example, here the set of X, Y, and Z. So then you just glue them and regard them as one single object we call a domain. And in fact, each domain encodes only one logical qubit. As you can see, for example, if this is for this domain, I get a measurement Z. But if I look closer into this system, if this spin is pointing up, that spin has pointing down because my construction is by singlet, so they are anti-correlated. And this spin would have been up, down, but there is the other possibility. In fact, these are the 2-dimensional subspace that encode the logical qubit. So the upshot is that each domain is only a qubit. So this, maybe you asked this question yesterday, what would be the computation of this code? 1 qubit, ideally we like to be on 1 spin, but it's delocalized into a several spin. Okay, and so once I identify the vertex, so that's this number. And the edges, E there simply is the number of edges connecting one domain to the other. Okay. But the edge for the graph state need to be reconstructed in a way that if you have even number of edges connecting to domain, effectively there's no domain connecting them. This is essentially due to the sigma z square to identity, because as in the graph state, the edges indicating that you are applying a control Z operation. And if you apply twice, essentially there's no action at all. And if you have a two domain with three edges, essentially you only have one. So you need to do this modulo 2. Somehow there's a Z2 operation here. So once you're done, you have to check whether your system is connected, well connected, so that you can identify path from one side to the other, or from top to down, and make sure that this lattice or this graph is percolated. If it's percolated, according to the percolation theory, then in a large system size limit, you will be able to find macroscopic number of them. So this is the connection also to the percolation theory. But we check how stable this connectivity is by doing percolation experiment, numerical experiment on the random graph. So how do we do that? For each vertex, we try to remove them with certain probability. And so what I've shown here is, suppose I generate this random graph, and I look at every side, I assign some probability to remove the vertex. If the probability is large enough, then the lattice is so hollow that I cannot find a path from left to right. So therefore, the probability of a so-called spanning cluster is 0. So I do this for different lattice size. This is for 20, give a curve like that, and 60, and 80, 100. There's a crossing here indicating that there's a phase transition. In fact, this is the usual percolation transition. So you can identify the critical point here. But the graph that we generated is sitting at here. We start with the graph, and then we start to delete them. So this shows that there are two different phases, two distinct phases. One is the so-called supercritical phase, the other is subcritical. In this phase, including the point here, is deep in the supercritical phase. So according to the theory of percolation, there you guarantee that you have macroscopic number of traversing paths. So this actually demonstrates. So I demonstrate this for honeycomb and square octagon. The random graph generating find my POVM actually is in the supercritical phase. Therefore, I can generate a graph that has sufficient connectivity, and you can show that you can actually, if you want, you can actually convert this random graph to a regular two-dimensional square lattice cluster state, but it's not necessary. So I've demonstrated you that the honeycomb lattice and square octagon and other lattice, the AKLT state can support a quantum computation. But there's a twist if you consider frustration in some lattices, like the star lattice or Kagome lattice, because the construction of the singlet correlation, I now know that if I want to assign an outcome XX here, it's not possible because this anti-correlation frustration. This is down, this will be up, but then this one is frustrated. So this means that these physical measurement outcome will not occur. And if you count the probability, the number of edges have some probability getting removed, and only 50% will survive. And in fact, this is smaller than the bound percolation threshold of Kagome lattice. The reason it's related to Kagome lattice is because this bound is always there. It's either external or it could be internal. But the triangle here, the edges could be removed. Okay. So we believe that the AKLT state on these star lattice, Kagome lattice are not universal. So we may wonder maybe there's some difference between these frustrated and unfrustrated AKLT state. Maybe they are in different phases. I don't know. There are some. If you want to generate the method to spin 2, there is a technical difficulty because to generate this naively, we don't get this sum up to identity. And so this indicates there will be leakage out of logical subspace. fortunately, we could add additional element here, and we were able to show that we're able to show and prove the equivalent, the corresponding probability distribution for the new POVM, and we were able to do some simulation and check that it's actually also in the supercritical phase. And so we were able to show that also the spin to AKLT state on the square lattice here is also universal. But the reason we constructed this is at that time we don't know how to do this for spin 2, so therefore we just modified lattice to make it simpler. But now let me summarize. So I introduced the model of quantum computation, in particular the measurement-based quantum computation, which use entanglement as a resource. And I demonstrate and show you how we prove that these various AKLT states on these lattices can be useful for quantum computation. There are also some questions you could ask. Could I deform the AKLT model slightly and you could still do quantum computation, or even sitting at thermal, some finite temperature where the thermal state can be useful. We don't have any result on that, but we construct some toy model that demonstrate there is some sort of notion of transition in quantum computational power, and that's the phase diagram. And I'd like to know whether the computation of AKLT state is related to whether it's belong to certain symmetry protected topological order. And more generally, in this symmetry protected topological phase, whether quantum computation can be performed similar to the AKLT. Okay, maybe I'll just acknowledge my collaborator. I'm missing a picture here, but I thank you very much for your attention.
A couple of short questions or comments.
Yes?
Could you say a little about the fault tolerance properties of?
Oh, fault tolerant property of this?
Yeah, I mean, is it fault tolerant or it feels a little bit irreversible in some ways?
So you can think this way. Once you get to the graph state in 2D, then you can use this to simulate error correcting procedure in 1D, one-dimensional circuit model. But for that model, the error threshold is very low. But if you could go to three dimension, for example, the spin to AKLT state, you can consider on the diamond lattice, then I believe you can generate a three-dimensional graph state, and then you can use the fault tolerance of 3D cluster state, and that will give you a quite high threshold.
So you're saying there's no subtlety about it's just fault tolerant.
Yeah. So in 3 dimension, the cluster state can be used to simulate the so-called surface code or surface code quantum computation. And basically, it simulates the measurement pattern will be topological in the sense that it's like braiding of these anions, and that turned out has been looked by Rosendorf and collaborator, and show that this actually gives a quite high threshold, about 1%, which is the highest so far. So you can imagine that this AKLT state in 3 dimension on diamond lattice, you can generate a 3-dimensional graph state and then convert it to a 3-dimensional cluster state, and from there you could use the scheme. So if the initial step, you can do it quickly because these measurements can be done simultaneously. So if that step can be done quickly, then this would later step can translate to that. Yeah.
Any more questions? Well, if not, let's thank the speaker again.
Thank you.
So we meet at 30 past.